Welcome, one and all, to Exploring Glass, a National Science Week event for 2022. My name is Broderick Matthews and I'm the STEM Outreach and Engagement Coordinator for Defence, and it's my pleasure to be here in the Japan Theatre at Questacon to host today's event with four amazing scientists. I'm ready to share them with you and how they work with glass in interesting and unique ways. We'll talk more to them in a moment though, but I'd like to begin by acknowledging some of the first people to use glass on the lands on which we're meeting today around this country, and they're the traditional custodians of the land on which we meet. Here in Canberra, we're on the lands of the Ngunnawal people, but I know we're beaming out through YouTube and we've got some of our scientists joining remotely across all the lands of this country. And so I'd like to pay my respects to elders past and present and extend that respect to any Aboriginal or Torres Strait Islander peoples who might be watching today. Aboriginal and Torres Strait Islander peoples are probably the first scientists for this land, and across Australia they certainly explored glass. They explored natural forms of glass, like obsidian to make cutting tools for many thousands of years. They also used Darwin glass, which is another form of natural glass found in Tasmania, and it's thought to be formed from a meteorite impact on Earth. And Tasmanian Aboriginal peoples used this Darwin glass to make incredibly sharp tools, and they've found tools dating back 27,000 years in Tassie, which is just amazing. Since working with natural glass, humans have then discovered how to create human-made glass, melting, blowing, colouring and shaping it to our needs. In fact, many of the earliest human uses of glass were just to make us look good. Glass beads were used as jewellery in Egypt around 5,000 years ago, and from beads, humans started to create vases, glasses, cups, exquisite, detailed objects that were beautiful. Coloured glass has formed beautiful stained glass windows in many of our Western buildings for hundreds of years. And especially curved glass has been used for thousands of years to bend light and correct sight for people. So glass is amazingly useful, it's beautiful, and it does some really interesting things. But we often take glass for granted, potentially because we look through it rather than at it. But today we're going to take a look at glass. And in fact, I want you to take a look around the room right now that you're in. How many different objects contain glass? Your windows, phone screens. I've got some camera lenses in front of me. Expensive bottles of water. They're generally made of glass. And there's hidden glass too, inside the optic fibres underground or on the solar panels atop your roof. I think it will be almost impossible not to find glass around you right now. 2022 is the UN International Year of Glass, and also the theme for National Science Week. Today, I'm excited to take our exploration of glass further as we talk to scientists and engineers about how they are using the wonderful material of glass. But before we meet the wonderful scientists who are sitting next to me here today and are going to take us into their cutting-edge work, it's my pleasure to introduce the top scientist of them all. Dr. Cathy Foley is Australia's Chief Scientist, commencing the role in 2021. With a background in physics and superconductors, Dr. Foley is not only an inspiring scientist, she's a wonderful advocate for women in STEM and super keen to support the next generation of scientists. It's my pleasure to welcome Dr. Foley to officially introduce today's event. Over to you, Dr. Foley.
And thank you so much, and good morning and welcome everyone. I'm so sorry I'm not there in person, but I hope you know that I'm there definitely in spirit. And it is a pleasure to welcome you today and to open the morning's event on glass. I have to say it's particularly of interest to me because my first job after I finished my PhD at university was working at CSIRO on a metallic glass where we cooled metal at 1,000,000 degrees a second, so it wasn't crystalline but amorphous, which is why we're able to see through glass. And we use that material for bone healing and low noise power amplifiers and transformers. So that's something which says that I'm really into glass. I'm sorry I'm not there to join you in the details. I'd also like to begin by acknowledging the traditional custodians of the land I'm coming from today. I'm up in Sydney and on the lands of the Gadigal people of the Eora Nation. And I want to pay my respects to their elders past, present and emerging. And I'd particularly like to acknowledge the value Indigenous people are bringing to science and technology and innovation, which we are really learning about and embracing. And I can't emphasise enough that Indigenous knowledge is absolutely substantial and that we must facilitate genuine engagement with our Indigenous communities, because knowing that we have much to offer, or they have much to offer for a sustainable future. And that's something we can learn from them, because they are the absolute experts in sustainability, being a continuous culture for many, many tens of thousands of years. So my job as Australia's Chief Scientist is to advise government about issues relating to science and technology and to champion science. And another part of my job is to promote the role of science and encourage people like you, our STEM leaders of the future, to follow your dreams. And I love this part of my job. I actually think it's the most important thing I do. We need young people like you for the jobs of the future. In fact, that's why I'm not with you today, because I'm actually at one of the round tables our Minister for Science is holding about digital tech jobs and how can we make sure they're there for you. Because jobs in the future will be in space, in defence, cyber and quantum, but also environmental consulting, biomedicine and advocacy. And everyone will need to have a level of digital skills, regardless of what you're doing. Active listening and creativity are also amazingly relevant if we're going to be successful as a society. And these things are not only just ambitions under the banner of, wouldn't it be lovely? We need your skills for these future industries. And this is a challenge, but it's also an opportunity. So what might your career in STEM look like? I often hear from students that they want to study medicine. And I actually have a daughter who's a medical doctor. She's an oncologist. So this is a really important career and very important. But people do medicine often because they think they want to help people, which of course is fantastic. But I want to challenge you to think of a successful STEM career and what it looks like, because it can also be something that can help people as well. And I want you to start dreaming big, because every STEM discipline opens up huge opportunities to better the world around us. Whether you're interested in IT, pure maths, chemistry, biology, even social sciences or physics, the world is your oyster. And there are many more pathways than you expect to be able to have a career in STEM. Did you know that the Australian federal government employs more than 20,000 people through our publicly funded research agencies such as CSIRO, DST, ANSTO, who you're meeting today? The role of government scientists is very important to the role of university and very different to the role of university scientists. Their role is to make sure our country is prepared for everything and anything. You probably know of CSIRO, the Commonwealth Scientific Industrial Research Organisation, and that's where I worked for 36 years. So it's something I know well. But before today, had you heard of the Defence Science and Technology Group, or Geoscience Australia, or the Australian Nuclear Science and Technology Organisation? What about the National Measurement Institute, or the Australian Institute for Marine Science? And so it goes on. Science opens many doors, and the Australian government relies on the cutting edge work of our scientists to create opportunities for us as a country. And you'll hear a lot more about that from the panel in a few moments. And as a final word, I know most of you here today are in high school right now. And as you head into senior subject selections, it can sometimes feel like choosing one path is forcing you to abandon all others, that the subjects you pick now are narrowing your options. But let me assure you that with each step you take in STEM, more doors will open. A lot of discoveries are made at the boundaries of different fields. And if you've got broad interests, that is a great thing. One of the most important pieces of advice I can give you is to follow your passions. Keep yourself open to the idea of new opportunities. There is no best STEM career pathway, but there are many, many brilliant and rewarding ones. So enjoy today, and thank you so much for letting me kick off your special event. So back to you.
Thank you, Dr. Foley, for that inspiring introduction. And it's fantastic to think about the many scientists around Australia that are helping to build our nation and helping people as well, and the different pathways that those watching today could take to get there. Now it's time to meet the 4 government scientists who are going to be sharing their work with class on this panel today. I'll introduce them one by one, and each will share a little bit about their work before we open the floor to questions to you, our audience. We've got some students in the theatre here with us. It's fantastic to have you here today. And I also know there are many people tuning in online. So please ask lots of questions as we go. You can type them into the live stream feed on YouTube, tweet them using the hashtag #ExploringClass, or we're going to be taking some from the people right here too. Now, our first scientist today is from Australia's Nuclear Science and Technology Organisation, ANSTO. ANSTO is Australia's nuclear centre of excellence and plays a role in advising the Australian government on all nuclear science and technology matters. ANSTO scientists investigate subjects that follow a wide variety of areas such as materials, life sciences, climate variability, mining and engineering. Professor Anya Paradovska works in the Australian Centre for Neutron Scattering at ANSTO. And I'll hand over to Anya to share how she explores glass. Thanks, Anya.
Thank you very much. It is so nice to be here, and it's my pleasure to introduce Australian Centre for Neutron Scattering at ANSTO and to share how we using glass for our science. So I am an engineer and material scientist working as a crystallographer, but I'm using neutrons to improve processes, 3D printing, welding, repairs. But to get neutrons to my instrument to do the science I wanted to do, they need to go through the guides. So our guides are super mirrors, neutron super mirrors. So they are designed to guide the neutrons from the reactor into our instrument so we allow to do the science and measure the properties of the materials that we're investigating. So in my role, I'm actually trying to build the bridges between the academia and industry and help industry utilize our unique neutron microscopes to see a variety of science, from food science to mechanical engineering, and all of this is done through humble glass. And glass for us is a unique material because glass doesn't react with other materials, so we can hold it in safely. Our nuclear medicine for majority of Australian is held inside the generator in a small glass container. Our guides are using silica as a substrate. We're using also a glass in instrumentation of our instruments to protect us from radiation. They can be material implemented and frozen in the glass that protect us from radiation and give us visibility. In terms of the materials characterization technique, we also very interested in glass performance. As Professor Dr. Foley mentioned that metallic glasses and sustainability of glass is of high issue for Australian community. So glass is the material that we can recycle very effectively. It doesn't use the strengths and properties, so we can do it this on and on. And I think there is an opportunity for us to also introduce novel ways of producing glass components through the 3D printing technology. And I think in the future, we will see this humble material approaching many other areas. And I'm excited to be, from the technological perspective, how our industry sovereign manufacturing will grow, our interest in glass will also grow with it. Thank you very much.
Thanks, Anya, for your very interesting reflections on glass. I'm keen to explore more about these neutrons as we go. I'm sure many of you watching might have some questions too, so feel free to start typing them now, but I'm going to continue to introduce the rest of our scientists here as well. The next scientist is joining us from the Commonwealth Scientific and Industrial Research Organisation, or CSIRO. CSIRO is the largest Australian government-funded research agency, and CSIRO tackles some of the greatest challenges facing our country through innovative science and technology. Dr. Taryn Sanders is a postdoctoral fellow in the CSIRO Oceans and Atmosphere team, and uses glass to better understand the world around us. Take it away, Taran.
Thank you, Broderick. Hi, everyone. I'm Tarun Sanders, and I'm a new postdoctoral researcher with CSIRO. My work at CSIRO looks at developing and testing new optical sensor technologies, ground-based, for monitoring different water quality parameters, such as nutrients like dissolved nitrogen in water. So it's important to monitor these nutrients because these nutrients can promote the growth of harmful algal blooms, which can block sunlight and deplete oxygen levels in the water for aquatic life. So some of the sensors I'll be looking at developing basically use light to detect these various water quality parameters. As some of you know, visible light forms only a small fraction of the electromagnetic spectrum. There are other forms of light like ultraviolet radiation and infrared, which you cannot see. And glass is integral in these optical sensors for the ability to manipulate light. So here's an example of a prototype, well, part of a prototype instrument developed at CSIRO, which utilizes glass. Here, glass is used for this fiber optic cable, which collects light reflected from a water body surface. The light then transmits to a lens, which collimates and directs the light to diffraction grating. And a diffraction grating is sort of like a glass prism, which basically splits the light into its spectrum, so all its different colors, which is then imaged onto a camera. And it's really important to look at the reflectance of these water bodies because different parameters and materials interact with light in different ways. So each material can reflect more light or absorb more light in a particular part of the spectrum. For example, chlorophyll in water bodies absorb more light in the red region and reflect more light in the infrared region. And from this, we can work out the concentration of chlorophyll and monitor these harmful algal blooms. So this is an example of a sensor which manipulates light. And my work will be looking at different ways to combine different glass components like diffraction gratings, lenses, fiber optics, to be able to sense different water quality parameters in addition to chlorophyll, for instance, dissolved nitrogen.
Wonderful. Thanks so much for sharing your work underwater there, Taran, and the way that you're using glass. Hopefully that's making all of you watching out there a bit curious to ask some more questions. Please keep them coming through. But I still have two more scientists to introduce. Our next scientist is from Defence, working in the Defence Science and Technology Group, or DSTG. DSTG is the Australian Government's lead agency responsible for applying science and technology to safeguard Australia and its national interests. Sinead Lay is a materials engineer from DSTG, and she also uses glass underwater, but in a slightly different way to Taran. I'll hand over to Sinead now to help take us further. Thanks, Sinead.
Thanks, Broderick. So at DSTG, we work on a range of different projects. But in my area, I work on designing different types of undersea sensors, which are used on things like ships and submarines. And the reason I'm here today is because the main type of underwater sensor that I create is actually made using glass optical fibres. Now, many of you would be familiar with glass optical fibres or fibre optics for things like telecommunications. This includes your high-speed internet and things like telephone and television networks. But for those of you who aren't familiar, optical fibres are very flexible, transparent, long fibres, most commonly made from glass. They are very fine fibres, sometimes only a little bit thicker than a human hair. Now, the cool thing about these optical fibres is we can use them to transmit data in the form of light via something called total internal reflection. So put simply, that just means that when we shine light down one end of the optical fibre, it is able to travel through that fibre by reflecting through the glass core like this, all the way until it reaches the other end. And we can use this technique to transmit information over really long distances at a really fast rate. And that's why these fibres are fantastic for things like telecommunications. Now, in my job, the optical fibres I work with are a little bit different. They have a special section of fibre in them, which is actually a fibre laser. And the unique thing about this section of fibre is it can sense whenever we bend or stretch it. So even when we move that optical fibre just a tiny amount, it changes the way the light waves travel through the fibre, which we are able to detect and measure. So what I do in my job is I incorporate that special section of fibre into an undersea sensor known as a hydrophone. And a hydrophone is just a special type of underwater microphone that we use to detect noise in the ocean. And the reason we do this is because it's really difficult to see underwater, especially if you're in deeper, darker oceans. We can't see much at all. So we need sound and hydrophones to help us navigate and detect things like ships, submarines, sea animals, pretty much anything that makes noise. So the way the device works is when a sound wave is travelling through the ocean and it hits one of these hydrophones, it exerts a pressure on that very sensitive fibre laser inside. This causes that fibre laser to bend, which changes the way light waves travel through the optical fibre. That then sends a signal to us to let us know, hey, something's making some noise in this area, and then we can go figure out what it is and where it's coming from. So that's how these sensors work. If you're interested in this sort of thing, I recommend listening to some of the recordings made using hydrophones for different sea animals on YouTube. The ocean's a surprisingly noisy environment, and even things like fish and shrimp can make some pretty unique sounds. So that's a bit of a crash course on fibre optic hydrophones and the sort of thing we do with glass at Defence.
Wonderful. Thanks so much, Sinead, for showing us yet another application of glass and a very different way of using it underwater. Now it's time to introduce our final scientist from Geoscience Australia. Geoscience Australia is the Australian Government's trusted advisor on the geology and geography of Australia. Geoscience Australia applies science and technology to describe and understand the Earth for the benefit of Australia and Australians. Dr. Saleh McAlpine is Director of Strategic Basins at Geoscience Australia, and she'll be sharing a bit all about the building blocks to make glass. But I'll let Saleh explain that further to you all. Thanks, Saleh.
Thanks, Broderick. Good morning to you all. In Broderick's introduction, you heard that Geoscience Australia covers the geology and the geography of Australia. So you might wonder why I'm here today talking to you about glass. Well, 90% of all glass is made up of silica. 70% of that glass is made up of silica. And what I've got here for you today is a beautiful sample of silica. Now, silica is a mineral. It is silicon dioxide, but those of you that love rocks and minerals may know this as quartz. So, I'd like to step back and talk to you about silicon now, which is the element. So that has the chemical symbol Si, and it is a component of silica, the mineral. Just for completeness, there is also silicone. Now that's the rubbery material that you might have in your kitchen, maybe a cupcake mould, but as delicious as cupcakes are, that's not the material we're talking about today. So back to silicon, the element, and silica, the mineral. You've heard from the other speakers that there are many ways to use glass, from the everyday to the very high technology. Silicon as an element is also being recognised as an element of increasing importance in everyday use, but also, most particularly, in these high-tech uses. The importance of silica is reflected for the very first time by being incorporated into Australia's critical minerals list. And a critical mineral is not a type of mineral, element or material. It's all about supply and demand. So as we need to tackle the challenge of climate change, for instance, the demand for this particular element is increasing. We use it in glass, we use it in solar panels, and there's an image behind me of an array of solar panels which contains a significant amount of silicon. So as we go through applying science to these global challenges, it's quite interesting to have an understanding of how the particular elements that we extract from the natural environment are incorporated into these. So as we move to a low carbon future in response to climate change, demand for renewable technologies such as solar panels increases, and the demand for the materials to make those solar panels or these other high-tech uses that the panel has introduced requires more of silicon and silica. So this is where geology comes in. How do we get more? Where is it in the natural environment? Well, it won't probably be of any surprise to you that beach sand is predominantly silica. Not everywhere in the world, but in Australia that is the case. River systems, quartz sandstones are often made of a lot of silica. Those are called quartzites. For rock nerds out there, there's dolomites and pegmatites. These have a lot of the mineral silica. And so you might ask me, well, I understand that there's an increasing demand for this particular material, but don't we have a lot of it? And the answer is yes, we have heaps. But for these particularly high-tech uses, to go into this particularly high-tech glass, we need a very high-quality silica, which is its technical term, a purer form. So those don't occur everywhere across Australia. And the role that Geoscience Australia plays is understanding the prospectivity of this particular mineral to be able to supply those that need it around the world. So this is an emerging industry in Australia, and it's one with lots of opportunity. So let's just project to the future for a moment. Australia is well positioned. It has a really interesting geology. You won't be a stranger to the fact that Australia has really exciting rocks and minerals and a lot of mineral prospectivity. It's really the foundation of a lot of the lifestyle that we enjoy today and the strength of our economy. Silica, and its increasing demand has a real role to play in the future prosperity of Australia. So Geoscience Australia is developing new programs to understand where this is, how does it form, what's the geological environment in which it's going to be most common, so that we can respond to the increasing demand across the world.
Wonderful. Thanks very much, Saleh, for sharing, I guess, the very beginning of it all, of where all this glass comes from. Now, we've heard from each of our scientists and know their areas of expertise, from neutrons to algae, fibre optics and silica itself. But now it's time to open the floor to questions from our audience. Please ask as many questions as you like, pop them into our YouTube comment feed, tweet them using the hashtag #ExploringGlass. For those in the audience here, pop your hand up. We've got a microphone to come round to you when you have a question. But while we wait for those questions to come flooding in, I'm going to take my privilege as host to ask the first question to our panellists. And I'm going to open the floor to a couple of you on this one. Can you tell me why glass is such an important material in the work you do? What makes glass better than using plastic or something like that? I might start with you, Anya. Why using glass and not plastic?
I think the biggest advantage of glass is the transparency. and also the fact that it doesn't corrode and doesn't degrade over the time. So when we build the instruments, in our case, we build them for 10 to 15 years. We wanted to make sure, and they in very harsh environment, radiation environment. So we wanted to make sure that they are performing over that period of time. The other advantage is that it's flat, and we can put coatings on it. So we can create these super mirrors, and that gives us significant advantage in terms of efficiency. In other case, for me particularly, is that I'm in the civil engineering environment as well, and architectural glass is also of significant interest. Glass is strong, is robust, and we can create different shapes and sizes on very small scale and large scale. So that gives it huge opportunity for architecture design, for mechanical design of the components, and I think there is lots of more to come in the near future from processing and reprocessing glass.
Fantastic. I might throw to you next, Taran. How about for your work? Why is glass so important?
As mentioned by Anya, glass is transparent to a wide range of wavelengths in the electromagnetic spectrum, which a lot of materials are not. And also, glass comes in many forms, types, and shapes. So, as mentioned previously, silica glass can come with different grades of purity, which can change its transparency in the electromagnetic spectrum. So when using it to manipulate light for use in optical components in these sensors. And there are other types of glasses like chalcogenide type glasses where germanium, selenium, and telluride is used, and that can transmit more light in the longer wave infrared type regions. And also, as mentioned, glass is very robust. So silica glass can withstand extremely high temperatures. It has a melting point of around 1600 degrees, which makes it really useful to use in a range of different environments with high temperatures, pressures, and so on.
Fantastic. Thanks, Taran. And maybe to you next, Sinead. Why is glass so important?
Well, as the others have already mentioned, glass has a really nice, unique set of properties that make it useful. So the transparency really allows us to use it to transmit information in the form of light. And we're really good at making optical fibres. So we can make them in such a way that they're able to transmit this data over really long distances without losing that signal. So they're really useful for the telecommunication industry and that sort of thing. In terms of why glass is better than plastic, there are some benefits. For example, plastic optical fibres don't transmit data as far. We need to repeat the process to get the same signal. For me personally, I want to put my optical fibres in the ocean, which means they probably will get wet. So we want to make it a little bit durable. And unfortunately, plastic optical fibres don't like water as much as glass. They tend to swell and degrade with time, whereas glass is quite inert. So it's good in all sorts of solutions, even pretty aggressive ones like acids or something like that.
Fantastic. All right, and I might ask a different question to you, Saleh. You talked a lot about the different forms of glass and the very high purity glass that we're getting and exploring around Australia. But is Australia well positioned in this market, or are other countries in a better place to produce this high quality silica that we need?
Oh, it's a very good question. There are many countries across the world with resources like this, but from an Australian perspective, we have excellent mineral endowment, and it's a really important role to play providing minerals to the world. And it's an opportunity for us as a country to be on that global stage. So yes, absolutely, there are many countries that produce glass. This particular sample that I brought in from the National Mineral and Fossil Collection today comes from China, and it's very well endowed country as well. So Australia has a role to play providing the global market, because this demand is real. It's going to take effort from everybody to be able to move into that renewable technology and low carbon future.
Fantastic, very exciting indeed. Awesome, we've got our first question from the audience right here in the Japan Theatre, so I might throw over to you to ask your question.
As a question for all of you, what made you want to be a scientist?
What made you want to be a scientist? Great question. Who wants to jump in on that one?
Or maybe I go first.
Yeah.
So I think the curiosity. Science is like a big playground for the adults, in my opinion. It's just that you have, if you have a curiosity and wanted to learn more things, you know, that's what we do it on a daily basis. We're practicing, like people practicing yoga. So you exercise in your brain and you learn different things. I think in my particular case, I was sort of good in maths and physics, but I didn't know what I wanted to do. I actually wanted to be a teacher. And because for majority of the smart females that I've been experiencing as young, I just saw the teacher. But when I went to the university, I was able to find amazing role models, male and females, who just show me the curiosity pathway to find passion and drive to improve people's life through science. And I think in my case, I'm optimizing aircraft components, structural buildings. I believe that I make a little contribution to our society and can help everybody through the engineering. Thank you.
Thanks, Anya. Maybe Saleh next?
Thank you for the question. It's actually very nice to reflect on what's brought us to this point. My personal story is simply a love for the natural environment. So I always was drawn to the outdoors and the natural beauty of the ocean or the sky or the rocks. I grew up on a small volcanic island in the Pacific called Norfolk Island, and it is a place of wondrous wild beauty. And it was that urge to know more, to understand how the earth worked, which got me into science. It's a natural curiosity.
Wonderful. And how about for you, Taran? What brought you into the world of science?
So I love my physics and maths from high school, and I like to solve interesting, challenging problems. So I did my PhD in engineering in University of Western Australia. And when I worked with solving these interesting problems, I worked across different disciplines. So I got to see what other people were doing in other fields as well. So every day is a bit different as well. You're working on something new and cutting edge, and that's what made me want to go into science.
Fantastic. And to you, Sinead, you've only recently started in your science career as such, haven't you?
That's right. I've just recently finished uni, but the reason I wanted to be a scientist was I just followed the things I really enjoyed. When I was at school, I enjoyed doing maths and science. I really loved the problem-solving aspect of things. And in science, that's what your career is all about. You're presented with a problem, and then you get the opportunity to be creative and try different ways to solve that. And it's really fulfilling at the end when you've come up with a solution that works and everyone thinks it's great, and that's why I do it.
That is a good feeling. You finally break through indeed. So don't forget, folks, if you do have questions for our scientists, ask them in the YouTube comment stream there, or tweet them using the hashtag #ExploringGlass. We've only got them for a limited time, so ask as many questions as you can. We've got another one in our audience, though, at the moment, so I might throw to them to ask their question. Thank you.
For the geoscience scientist, I have a question. Do you know how much silica is mined in Australia every year?
It's actually a very good question. What I can tell you is that we are at the very beginning of this industry. So there isn't a lot. There are some very prospective deposits in both Tasmania and Western Australia. But no, in many ways, this is an emerging industry. So a lot of opportunity on the horizon.
Very exciting indeed. Awesome. Well, I might ask a question to you, Anya, because I want to go back to these mirrors that you're talking about reflecting the neutrons. Because, I mean, fibre optics, I can imagine. We've got a fantastic demo of silica here. Taran's talking about underwater and algae. I can envision those. What does a neutron beam look like when you're reflecting those using your mirrors and your guides?
Yeah. So actually, I'm thinking like, because everybody knows how the fiber optics looks like, now multiply this by 1,000. So something around 0.5 meter by 0.5 meter. That is the neutron guide. Yeah, and inside of the neutron guide, there will be these super mirrors coated glasses, and then there will be lots of shielding. So to protect it from the radiation, to protect people from the radiation walking around, and also instrumentation. So these super mirrors are actually nickel and titanium coatings. Is a composite material that allow us to for neutron, because of like light, neutron scatters all over the place, and we want them at our instrument to be focused, so we can penetrate our samples with very, very bright beam. So we wanted to make sure that we not lose any neutrons on the pathway, because there is a gold rule for every instrument. Closer you are to the reactor, the more neutrons you have. But I work on the instrument that needs a resolution, so I'm like 40 meters away. So I wanted to make sure that I'm not losing all those neutrons on the way, and I can sort of guide them through this guide hole to make sure I have as many as possible, so I can use the science very, very efficiently.
Wonderful. And awesome. That's really interesting and amazing to think about guiding these. I mean, they're minuscule particles, aren't they?
That's right. Tiny, very tiny.
Awesome. We've got another question in the audience here. Over to you.
I've also got a question for all the scientists. What science classes did you guys take during high school or college?
Yeah. Let's start with Sinead.
It's the freshest in my mind.
That's right.
So in high school, so I went to high school in Victoria. So the rules are a little bit different state to state, but to do a science degree and then a science job, you had to do maths. That was a requirement. And then I did physics and chemistry. So I think I did a bit of everything. I didn't do biology, but that's also a good option. At uni, I studied materials engineering. So that's focused on a range of different things. That's got mechanics and maths in it, but there's also individual units focused on the properties of different materials. So I did a unit on glass, and I did a unit on metals and alloys and that sort of thing. And then when I finished, I could decide which one I liked the most and specialise. So I just ended up in glass.
Fantastic. Maybe Tara, do you want to go next, mate?
Yeah. So I did my high school in Western Australia, and in year 11 and 12, I chose subjects like geometry and trigonometry, calculus, physics and chemistry, and the standard English as well. So that the maths would be equivalent to your maths specialists and methods now as well. And then in university, I did a bachelor's degree in electrical and electronic engineering, simply because I knew there was going to be a lot of maths in it, and I really loved my math from high school as well. And then I went on to do a PhD directly, and that was with the Department of Mechanical Engineering. And this is where I also worked with glass, particularly coherent optical fiber bundles, which are basically fiber bundles containing many thousands of fibers. And I use these for transmitting images as well. So that was a totally different area that got me into the optics and glass field.
Very exciting. One form of glass to another. I love it. Saleh.
Not dissimilar, actually. A lot of mathematics, physics and chemistry. I went to university to study astrophysics, but what happened to me very quickly was a little bit like Dr. Foley said, it was the intersections between disciplines that really got me excited. So I was able to apply my love of physics, chemistry and mathematics to the earth. So I took the route of geology after that. And I went through and did my PhD as well, and that was on the particular minerals in the Earth's mantle.
Very exciting. And finally, Anya?
So I actually, my first, I'm Polish, yeah, so I did not experience high school here, but it is not very different to what, as I have children in high school, I can see we go through the same process. I wanted to have a career with no borders, you know, like that I can travel and experience the world. And I have to say that engineering gave me that opportunity. Like my colleagues, I'm a material science engineer, and then I did a PhD in mechanical engineer. I work in Oxford in UK, and then I came to ANSTO in Australia. I can go and work anywhere in the world. We speak the same language. So it's actually, for me, the ability to learn maths and science, as well as communicate our discoveries and our challenges in science with others. That's what really puts a mark for me for moving into the engineering space.
I love that. A career without borders as a scientist and engineer, that's definitely true. And maybe that leads to my question that I want to ask, which is where have you been that's interesting to do some testing for your work? I might start with you, Sinead, actually, because you're taking these fibre optic sensors, you need to put them underwater. Are you going out into the ocean off of Adelaide there?
Yes, that is part of the job. So it's all well and good to develop something in the lab, but we need to test it. So in my job, there is a fair bit of trials work where we get to go out to see and deploy some of these devices and see how they perform. Sometimes we will do a quick trial. So I'm based in Adelaide, so we might take our equipment down to the Barossa dam they have there and test them out where it's nice and quiet first before doing a big ocean trial. But yeah, there is a fair bit of field work involved.
Yeah, very exciting. And in your work, Saleh?
Yes, there is a lot of field work and travel opportunities in geology. I've had the great privilege to travel to many different countries because my particular study was understanding the mantle through rocks that erupt in volcanoes. So there's some really beautiful volcanic arcs around the world. With my work at Geoscience Australia, understanding the mineral prospectivity of Australia in particular, we deploy a variety of techniques to understand the Earth. Some that we use to understand mineral prospectivity include geophysical methods such as deep crustal seismic or drilling, just like Sinead, to be able to test our theories. So it's we might take a drill rig into frontier areas in Australia to really understand the geological context. So I've been many areas in my career. One that springs to mind is when I ran a drilling program in the Nullarbor Plain to understand the mineral prospectivity out there. And it too was a very wild and frontier environment in a very different way. But yeah, it's a discipline that does lend itself to understanding the world around you in quite a nice no borders type of way.
Very exciting.
Turbidity, which is the clarity of the water, and so on. So that was one of my recent field trip experiences, which I got to, had the opportunity to participate in CSIRO.
Fantastic. And I'm presuming field work for you doesn't happen much because you have to stay where the neutrons are, right?
Yes, I have to. I'm attached to the large-scale facility, but they are built in some amazing places. So we are only 30 minutes from the beach, and then, for example, there is a ILL in Europe, in Alps, and I've been into some amazing places in Canada and US. And I really enjoy it. But I think particularly at ANSTO, for me at the moment, is that we are international facilities. So people come from all around the world with roots of their science to use our unique facility, and we were able to help them to push the technology or the material that they are currently discovering to characterize and optimize. And I think it is amazing because before they start annoying you, they're going home.
Amazing. No, that's really exciting that all our science right here in Australia is reaching out around the world and doing amazing work. We've got another question from our audience, so I'll throw it up to our audience member. Thank you.
In regards to from CSIRO, sorry, how large of a surface area can your sensors monitor? You were saying that it could monitor some of the algae blooms. How large of a surface area can it monitor? Is it mostly just in the ocean, or are you looking at fresh water? What particular?
So with my work, I'm looking at both fresh and coastal waters, and the sensors which I'm looking at are ground-based, and they basically look at a single point on the surface of the water. And some of the sensors I'll be looking at developing will be submerged in the water, and you can look at different points by adjusting the depth along the water column. Again, these are single point measurements as well. So you'll have to have a number of sensors across the water body to look at multiple points. However, other people in my team are also developing satellites-based telescopes, which also look at these water bodies as well, and work in conjunction with the ground-based sensors. So the satellites can look at basically the entire water body at a lower resolution, but across a wider surface area as well.
And is there glass on those satellites, Taran?
Yeah, there's glass there as well. So the telescopes use different optics and lenses to focus the light. There's also a lot of mirrors, like off-axis parabolic mirrors, which help relay the light to hyperspectral camera sensors as well.
Yeah, it really is everywhere, even up in space. We've got another question from our audience. Thank you.
I'm really interested in climate change, and particularly you're talking about glass as a property, and I'm sitting there and I'm looking at plastic water bottles, and I'm thinking about microplastics in the ocean where, you know, your work gets done. So I've got sort of one question, which is that kind of, you know, you can keep recycling glass. So can we get to a point where glass, we don't have to keep digging it out of the ground. We can produce enough and just keep recycling it so that actually we're not doing more environmental damage, you know, in the long run. So that's my first question. The second question is also around, well, like you're saying glass is really robust at its, like, it deals with like heat really well and stuff, but if I drop a glass, it breaks. How do you make glass flexible and strong if we're going to really use it, like, to solve some of these issues like reducing plastic?
Well, do you want to start us off? Yeah.
Yes, I'll give a very simple answer to the first question that you had. The answer is absolutely. One of the other people in the audience today asked about, you know, do we currently produce silica in Australia? Well, the other market that is really available to us is absolutely recycling. We have a lot of solar panels in this country, and as the technology improves and the solar panels get smaller or thinner, or people want new ones, that's a huge market. So there is certainly a part that Australia can play in the circular economy to be able to mine less or complementary market of recycling. So that is absolutely something that is discussed and quite active, yes.
Well, that was actually a question we had from Cam in Melbourne online, was, is recycled glass usable in any of your work? Or are you after like the really high quality stuff?
I think it is definitely very usable because glass does not lose the properties. You can achieve the same strength. The only problem with glass that we're having is that the reprocessing is is not yet energy efficient. So there is a lot of work put into it to make these processes as efficient as possible, because the markets are there. There will be more solar power, where probably we will be putting coatings on every windows in Australians' homes to make them solar efficient in the near future. So definitely recycling of glass is of high importance and high interest in terms of the global and Australian economy. I think at the moment we are very focusing on a very fundamental discovery stage in recycling. Even though we're recycling glass for many years in the past, I think the key is to actually find the unique solutions for, because it's much more, we don't want to print bottles or things like that. This process is already efficient, but finding this unique opportunity for glass, for electronics, for space applications, for fiber glass composites or metallic glasses opens completely new market and opportunity for significant technological advancement. So I think in the near future, this will be something that I hope that this generation over there will be thinking about recycling of glass in a very completely way than what we're experiencing now.
That's a great challenge to put on everyone in the audience. Did anyone have any ways to answer the second part of that question on how you strengthen glass?
I can answer that.
Yeah.
So optical fibres are really flexible, and that's an important property for them. We want to bend them and put them in cables along the ocean floor and all sorts, so they need to be flexible. And what makes them flexible is two separate things that work together. The first one is just the dimensions of it. When we make a material extremely thin, it becomes flexible, and that's simply because when we bend something small, those atoms on the outside have a shorter distance to stretch. So it won't break as easily because they're not being pulled apart as much as a thick material if you bend it. So that's the first component. The second part is when glass breaks or shatters, it will always initiate at a defect site on the glass. And it's the weak point. But optical fibres are made in a really controlled way, so we have this beautiful surface on them with very few defects, if any. And so they don't have weak points to break. So that also helps them in that we need a greater force to break an optical fibre than we would if it was covered in all sorts of defects. And if there are any defects, we also put a polymer coating on the outside of the optical fibres that kind of fills in the little defects and just gives them a little bit more protection. So that's how we can make it flexible.
Fantastic. Thanks, Sinead. Now, we're almost coming to the end of our session today, and I'm sure there are many questions out there. If you have asked a question on the YouTube or Twitter feeds, we'll do our best to answer them and post the answers in the YouTube description following the event. But for now, I've got one last question for each of our panellists, and I'm going to ask you the same question for all of you. What excites you about the future of your work and research with glass? What does the future hold? I might throw to Taran first to answer this one.
Yeah, so as I mentioned in my introduction, different materials interact with light in different ways. So I guess what excites me about the future of glass is developing different types of sensors, different ways of combining different components of glass to be able to sense different materials in the world around us. Also, I'm quite interested in the space stuff, which some of my team members are working on as well. And where one application is where these telescopes look across broad areas and take images across a wide spectral range to be able to image for monitoring for agricultural applications or monitoring water bodies and looking at the different spectral signatures or fingerprints of different materials as well in the world. So that's what excites me most about glass in my work.
Thanks, Taran. And maybe you next, Sarlo?
Yes. Well, there's a couple of things that excite me. I think that understanding the fundamental geology of how the minerals are formed that are so essential for the glass components is whilst there is a lot known, there's still so much more to know. And there's so much more to understand about the continent of Australia on which we live. So I think that fundamental mineral formation question of silica going into glass is one for me. And the other one is, as we as we look for solutions to combat climate change, the fundamental role that minerals plays in that and the appreciation of that is something that I'm quite passionate about, because it's such an essential thing to move towards a low carbon future. But the materials we need to do that, the materials we need for those solar panels, and the recognition of that, and the fact that Australia's critical mineral list is reflecting that, is something that I'm very much looking forward to working with into the future.
Thanks, Sally. I think we had a couple of technical issues there, but we'll push through. We're almost there. Sinead, what excites you?
I think the thing that excites me most is the new sensors that we can develop. We're always trying to improve the current technology that's already out there. We want sensors that are smaller and lighter, ones with greater durability that live longer. So I'm excited to see what we can come up with to improve the technology that's already out there and make the best sensor ever.
Very exciting. And Anya, to finish us off.
So I think I am excited because we are just speaking to technological excitement in processing of the glass and reprocessing of the glass. And I think recycled glass in the future will be part of our circular economy. And as it doesn't lose the properties, the potential is endless. And I think as much as conventional processing of the glass will be growing as the sovereign manufacturing in Australia will grow, I am really excited about 3D printing in glass, because that will open new areas for us in terms of the sensing, new sensors, new electronics, and the potential to create very complex shapes. And I think that will give potentially we can look at the internet and find those complex shapes already, but the application is yet to be discovered. And I think that using neutrons for us to testing these processes is of really quite an important opportunity for the next generation and us to make sure that we have a sustainable, a bright future, recyclable future, reusable future.
Indeed. There certainly are some fantastic challenges for the future that are being put forward to the next generation of scientists and engineers who I hope are tuning in today to this fantastic event. Thanks again to all our scientists for taking part today, to Anya, Sinead, Saleh and Taran. It's been wonderful to have you here, and thanks very much to Dr. Foley for joining us at the beginning too. I hope all of you who are watching today are excited about the future and the many interesting things we're going to be doing with glass. It's a historic material, but there's plenty to do with glass coming up in the next decade and potentially hundreds of years too. Thanks again to all the organisations who supported this event: ANSTO, CSIRO, Defence, Geoscience Australia and Questacon, the National Science and Technology Centre. I hope you enjoy the rest of your National Science Week for 2022. My name is Broderick Matthews. Thanks for exploring glass with me. Goodbye.